Hello everyone, welcome to the session on electromagnetic fields and transmission lines. We are discussing about Gauss law, and in previous session we have discussed the parameters regarding Gauss law. Today we will see the applications of Gauss law. Gauss law is a very interesting and simple law which based on the simple statement that flux passing across any surface is equal to the charge enclosed on that surface. So here now we will discuss about the applications of Gauss's law. So here we have to see the applications of Gauss law. Before that, we will have something to develop the imagination regarding the charges and the setup we are using. For easy understanding, we are using some 3D images and 3D setups, and in the same concept, we will try to develop some imagination power, imagination tricks which can help us understand this topic more easily. Now, if we consider a charge, either electron or proton, it is a tiny small particle, can be represented by a small point. Suppose a single point like this. These points can be considered as the charges. These charges may be present in space. If you see these charges, they are tiny particles, we can't even see them, but they may have some charge, positive or negative, positive, negative. They will have the sense of attraction and repulsion based on the charges. What is that basis? If there are similar charges, they will attract each other, and if there are opposite charges, they will attract each other, right? That is what happens. Now, if we consider a small point charge, and if you zoom it, you expand it in all the direction, what will be the shape of that charge? The shape of that charge will be nothing but like a big sphere. So that is also a reason when we consider a charge, a case of charge. Suppose if we want to see the application of Gauss law from Coulomb's law in case of point charge, then we take its area as the area of sphere. What is the area of sphere? It is 4 pi r square. So far what we have, we know these all are related to D. D is flux density, can be given by cos of density by differential area or surface, and from here we can say d phi is equal to d dot ds. We can write bar as d and ds both are vectors, and from here we can say psi is equal to integral of d bar dot ds bar. Okay, now let us consider the example of this sphere, the case of point charge, where we have to prove the Gauss law. Again, the same statement we have to prove. Let us consider that there is a charge at the center of the coordinate system. So there is a charge at the center of coordinate system, and that is a point charge. So what it will do, it will send out the electric flux lines in all the directions. So as we know that there is close relation between D and E. D bar is equal to epsilon E. So this relation is used here, and as we can see, at the center of this system there is a point charge. Now this point charge is crossing, sending out some signals. Those signals here we are considering as D bar, and this D bar we are taking as normal to the surface. So it emerges from the surface of point charge, and it is crossing out in normal way out of the sphere. This sphere we are applying Gauss law, so we will call it as Gaussian surface, and we are considering small differential surface ds bar on it, right? So we have d bar and we have ds bar for spherical coordinate system. So if we expand these points of differential surface on the floor, so those angle, that angle, say let that angle is d theta. Now this d bar, according to the Gauss law, what he says, d bar is cos, who is creating it, a point charge, say point charge q. And what is the area? Area for a point charge whose sphere is 4 pi r square going into the radial direction, in the direction of radius. So this is what we have. We have to just prove psi is equal to q. That is the first case of Gauss law application. So now if we consider this diagram, we normally take it as normal, but it is not mandatory that it must be normal. It may be in some cases given as some angle. So here we can see in this example, here some angle theta is given, and in this case D is going like this with some angle theta. So for this, what will be the component? It will be d bar dot ds bar, and the horizontal tilt component, say cos theta. But if we consider normal component, our mathematical complications can reduce. If this is perpendicular normal with 90 degrees, so here we can say this one is nothing but d bar dot ds bar. Okay, now this ds bar, differential surface. Now if we consider the coordinate system of spherical coordinate system, which constant plane it is? This constant, this surface, we are considering this surface, outermost shell of the sphere, and somewhere here there may be the radius. So if we take this line like this, So what is the value of, which value will be constant on this surface? Of course, radius. If radius is 10 here also it will be 10. Here also it will be 10. So all over the radius of this system will be same. So it will be the radius constant surface. So in coordinate system we have seen all the differential surfaces formulas. If you remember, these are where r is constant, radius constant surface. So it is given by r square sine theta d theta d phi. Now in this case, this is the ds bar. Okay, so let us further derive this expression. So let us see the steps. Let us keep them in the formula and let us do some mathematics for the proof of Gauss law from point form. Let's say what we have already we have ds is equal to r square sine theta d theta d phi, and d is equal to, say for this charge we can have 4 pi r square into ar cap. For this also we have to keep the direction ar cap. Now if we want to find out the flux phi. What is flux phi? Flux phi is nothing but integration of d bar dot ds bar. So this d bar we can keep here, this ds bar we can keep here, and we can find out the derivation. So we have to derive for these two terms, phi and theta. So double integration will be involved. So here one more thing we have to remember, what are the limits for spherical coordinate system. In spherical coordinate system, if you remember, in a spherical coordinate system there are 3 parameters which define some point P. So for defining them, what we require is radius r, then we require some angle theta, and then we require some angle phi. So radius can start at the origin and it can go up to infinity. So that will be limits for r. R will be from 0 to infinity. Theta, say it is the half circular calculation. So theta will be from 0 to pi, and phi is the complete circulation, that is given for 0 to 2 pi. So for this we'll keep the limits. So this psi will be equal to double integration of, say for 1 for 0 to pi, 1 for 0 to 2 pi. This value is q by 4 pi r square, and then r square sine theta d theta d phi. So here we can see r square gets cancelled, and product of these two similar directions, product of similar directions will be equal to 1. So that term will also go. The remaining term, if we take derivative for theta, it will become d theta will become only theta, and we can put the limit. Say we'll take out the constant, say we have q upon 4 pi. So one bracket will get, say, d theta, this theta limit from 0 to 2 pi, and then we will get sine phi d phi. So if we further solve this, we will get psi is equal to q by 2, and if we put limit for the integration of sine, that is cos phi, we will get minus of minus 1, then minus 1, that 2 will get cancelled, and finally we will get psi is equal to q. That is the point form of Gauss law. This is the first application we have derived. Now let us see some case where we will see the electric flux density due to some charge carrying conductor. So let us discuss it. For that, let us have one diagram. We have to consider a conductor, current carrying conductor. So let us imagine one current carrying conductor is there. Say this is the current carrying conductor, and on its surface we will consider small ds, out of which some psi or its d bar is passing. So already what we have established is psi is nothing but equal to q, equal to integral of d bar dot ds bar. Now conductor is a spherical coordinate system. Conductor is a cylindrical coordinate system. So for cylindrical coordinate system, if you remember, we have the coordinates as, say, this is the cylinder. So one parameter will be r from the line of z axis. Second, we require the angle phi. Third, we require the height z. And what are the limits for r? R limits are from 0 to infinity. The phi distance is from 0 to 2 pi, and z is from minus infinity to plus infinity. And we have also discussed the differential surface of cylindrical system. So at the surface, which constant plane it will be? Either we can have surface constant plane, radius constant plane, or angle constant plane. But in this case, this one is the radius constant plane, dsr. So the dsr will be product of other two terms. So this value is given by r d phi dz. So in place of ds bar, we can keep this value with direction going in radius direction. So this one will keep in the expression. So we'll have, say, psi is equal to d into r into d phi dz. We'll have one ar cap for this, we have one ar cap for this. Dot product of both of them will become 1. So we'll write only this expression. Now what will be the limit for z? This is not infinite line, it is a finite. So for z, say we'll take height of conductor, say from 0 to L. So this is the z here, and of course phi, angle phi is complete rotation 0 to 2 pi. So we'll keep them. So it will be psi equal to 0 to L, 0 to 2 pi into d r d phi d z. So now further we will simplify it and we will relate it with electric field intensity also. So we have, say, psi is equal to q is equal to d r. First we'll put limits 0 to L for dz, and second limits for 0 to 2 pi for d phi. So if we put the limits, we'll get dr z 0 to L and phi 0 to 2 pi. So further if we solve this, we'll get d r L 2 pi. Now this is our psi is equal to q is equal to this expression. Now one more thing we have to connect with this, another kind of density, that is charge density. We have to see the expression for this. Now our case is of a cylindrical surface. For cylindrical surface, there is line charge density rho L. Now this line charge density is given by cos, that is charge per length. So if we consider the charge and length from here, we can say that q is equal to rho L L. Now this is q is equal to rho L L. Now in place of this q, we can keep this value. So what we will get? We can write, say we can write rho L L is equal to this term d r L to pi. So from here, if we want to find out d is equal to, so what we can say, d will be equal to rho L L divided by 2 pi r L. So this L will get cancelled. So what we will get? We will get d is equal to rho L divided by 2 pi R. If we write D bar, it will be AR cap. Now same kind of answer we got in the previous chapter, previous sessions, when we discussed the line charge density with respect to electric field intensity in the topic of electric line charge density in the case of electric field. At that time we got some formula for line charge. Now we will compare it with the relation. What is the relation between D and E? D is equal to epsilon E. So what was that expression? For E, we can write in that expression rho L by 2 pi epsilon naught R into AR cap. This is the same derivation we got in that topic with some other method of solution. But from here also we can find it out. So we will stop with this topic here. In next session we will continue furthermore about this and the problems on this chapter. Till then, have a good day. Thank you.